So this is homework 10 question 2. For this we are supposed to collect the definitions of properties of various stochastic processes. So WSS process, we have seen this many times in the past over many homeworks. So basically the two defining factors is that the mean of a WSS process stochastic variable xt is 0 and the autocorrelation is a function of r tau, where tau is t2 minus t1 or t1 minus t2. Yeah, and so one very interesting fact it is r tau is the average power of signal at t1 when basically we take rt1 and if the input signal is a WSS process, the output is a stable WTI system. Of a stable WTI system is also WSS, wide strength stationary. And we come to independent increment process. So much like in the previous question where we studied, I think, Poisson increment process, if I'm not wrong. Yeah, Poisson increment. It's very similar in concept. This is the more general broad case, where here again, as in Poisson increments, we have T1, T2 and T3, T4 are non-overlapping and are hence independent. That is xt1 minus xt2 and xt3 minus xt4 are independent when t1, t2, t3, t4 are non-overlapping. So example is, as I told you, Poisson process, random walk, Wiener process, etc. So Markov process is pretty interesting and we encounter it a lot. In a Markov process, the past has no influence on the future given the present. That is, in other words, you can say basically every state depends on the previous or parent state and it doesn't depend on the states prior to that, right? So as you can see, probability of xn given xn minus 1, xn minus 2 dot 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 x1. So as I said, that the probability of a state depend only on the parent state, right? The parent state is xn minus 1. So that's what I've written. So examples are Poisson process, Poisson impulse, semi-random, random telegraph, random walk, Wiener process, etc. Normal or Gaussian processes. Now, this is a very general broad case of stochastic processes. Wiener process is an example, specific example of a normal or Gaussian process. Here xt is normal, as you can see I've defined it, if xt1, t2 dot 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 xtn are jointly normal for any n and any t1, t2 dot 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 tn. This is how the density function is given. Next we come to strict and stationary. For strict and stationary, this is a more you can say strict definition of stationarity than wide sense stationary, and here basically the density function of joint density function for x1, x2 dot 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 xn at time instance t1, t2 dot 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 tn remains the same if you shift it in time by epsilon, if you shift all the time instance by epsilon. As you can see, t1 plus epsilon. So statistics remains the same, or the density functions remain the same even with a shift in the time axis. Next we come to white noise. So if Wt is a Wiener process, then the derivative of the Wiener process is you can say white noise. So as you can see, these are the properties. Derivative is Gaussian white noise with zero mean, and impulse correlation, autocorrelation function. As you can see, I've listed them here. So you can say that stochastic process is white noise if the mean is 0 and the autocorrelation function is an impulse autocorrelation function, right? So mean ergodic, this is the definition of mean ergodic in MS sense, mean square sense. And finally, for martingale processes, we can say that stochastic process martingale, if the conditional mean, that is xt given xs equal to x1 is equal to x1, that is the conditional mean is equal to the condition itself. This is the condition, x1 is the condition, so the conditional mean is equal to the condition itself. Random walk and Wiener processor are examples.